Actually, we have derived an expression of EMF which is induced in a single multi-turn coil in our previous lecture. So, in this lecture also we will continue with the derivation of expression of induced EMF in a single multi-turn coil, which is induced in a coil which is inside the rotating electrical machines. Now, actually, we are interested in deriving an expression of induced EMF in a single multi-turn coil which is placed on the rotor and it is rotating, and of course since the rotor is rotating, so the multi-turn coil is seeing different flux density. So let me first of all make some recapitulation. These things were told in my previous lecture class, so I just will be making a quick recap. So you can see this is the cross-sectional view of a two-pole rotating electrical machine, and both the stator and the rotor are cylindrical in geometric shape. That's why when you are taking the cross-sectional view, it is appearing as a circle. So stator core is a cylindrical structure, and since we are taking the cross sectional view, the cross section is taken along a plane which is perpendicular to the shaft axis, so we are seeing this as a circle. Likewise, the rotor is also a cylindrical structure, so when we are taking the cross sectional view of the rotor and the cross section is taken along a plane which is perpendicular to the shaft, it is also appearing as a circle. And you can find that flux distribution, the magnetic flux distribution has been indicated for these two number of poles, that is one north pole and one south pole, which are developed on the stator core. And further what you will find that if you just apply Ampere's circuital law and take the developed view of the coil, and if you just uh, plot the space distribution of mmf, that is the magnetomotive force, it will come like this for a single coil. So what we have assumed is that it is no doubt that actually the distribution of mmf, that is magnetomotive force, or you may also replace this mmf by magnetic flux density, that means b. Only you need to do some kind of scaling on the y axis. So the distribution of magnetic flux density or mmf along the air gap periphery for this single coil is not sinusoidal. Actually, it's not sinusoidal. Actually, it's your rectangular in nature like this. But what we are assuming is that we are applying Fourier series expansion, and by applying that Fourier series expansion, this rectangular MMF wave is actually expressed as a summation of large number of sinusoidal wave, and out of those large number of sinusoidal wave, that sinusoidal wave which is having the same time period as that of the rectangular mmf wave, that sinusoidal wave which is having the same zero crossing and same time period as that of the rectangular mmf wave, that sinusoidal wave will be termed as fundamental component. And yes, there will be harmonic components also, because Fourier series expansion says that this non-sinusoidal waveform is represented by summation of summation of large number of sinusoidal wave. So we are only considering the fundamental component, and of course there will be harmonic components. That means you will have another waveform distribution for mmf, or even you can replace the mmf by magnetic flux density, as I was saying earlier. So you will have a huge number of sinusoidal wave, but those sinusoidal wave will have a time period which is less than the time period of the rectangular mmf wave, and those sinusoidal wave which is having time period less than the time period of the fundamental component, those sinusoidal wave will be known as space harmonics. So we are simply ignoring the space harmonics, and that's why it is not indicated in the diagram. Space harmonics are not indicated in the diagram. Now We can also view over here that if instead of this one coil, let me show it over here. Here we have only one coil. You see, one coil side is on this part of the stator core, which is carrying dot current, and another coil side is on this part of the stator core, which is carrying cross current. So for this single coil, the MMF distribution is like this, rectangular in nature. So if we have say three number of coils like this one, so if you have got three number of coils, then you will have MMF distribution for each of the coil. That that means for coil 1 dash, you will have the rectangular MMF distribution. Then you will have rectangular MMF distribution for coil 2 dash. Then you will have rectangular MMF distribution for coil 3 dash. So what is the basic idea? The basic idea is that we already know, or rather we have derived very thoroughly, that the nature of space distribution of MMF, or nature of space distribution of magnetic flux density along the air gap periphery for a single coil is like this, rectangular. So if you have got three number of coils like this one, so you apply the principle of superposition. That means you assume that when coil 1 dash is carrying current, then the remaining two coils are not carrying any current. Likewise, when coil 2 dash is carrying current, then remaining two coils are not carrying any current. In this way, if you apply, then you will be able to plot the nature of MMF variation, or let me say the word space distribution of MMF variation. For this single coil 1 dash, it will be rectangular, but for coil 2 dash, it will be rectangular. But what do you notice is that it is getting shifted by one slot pitch. You may refer to the diagram. So the MMF distribution for coil 2 dash is also rectangular in nature, but it is actually shifted by one slot pitch. So you may follow the mouse pointer, please. You see, this is the center of slot number 1, this is the center of slot number 2. So distance between this slot number 1 and slot number 2 will be termed as one slot pitch. So the MMF distribution for coil 2 dash is starting from the center of the slot number 2. So it is phase shifted by one slot pitch with respect to the MMF distribution of coil 1 dash. Likewise, the MMF distribution for coil 3 dash, the MMF distribution for coil 3 dash will be also rectangular in nature, but again it will be shifted by one slot pitch with respect to coil 2 dash, or it will be shifted by two number of slot pitches with respect to coil 1 dash. So that way we have just drawn the MMF distribution for each of the three coils, 1 dash, 2 dash, 3 dash, and when we are drawing the MMF distribution for each coil, we are making the assumption that the other two coils are not carrying any current. Now, since all the three coils are carrying current at a time, or simultaneously they are carrying current, so we need to simply add the ordinate, that is the y-axis value ordinate for the MMF due to each of the three coils. That means we will add the MMF due to coil 1 dash, we will add the MMF due to coil 2 dash, we will add the MMF due to coil 3 dash. So we will end up with this kind of MMF distribution, which is known as stepped MMF waveform distribution. Now, this stepped MMF waveform distribution can be further simplified or approximated by another waveform, which is your trapezoidal MMF distribution. So what do you basically observe here is that if you are having only one coil over here, if you are having only one coil over here, the nature of MMF distribution is like this, rectangular. Whereas if you have three coils, then the nature of MMF distribution is trapezoidal, because all the three coils will separately have the MMF distribution which is rectangular. So if you add the MMF distribution due to each of the three coils, if you add the MMF distribution due to each of the three coils, then you will end up with this kind of stepped MMF wave, and further this is approximated by a waveform which is known as trapezoidal waveform. So what is the basic merit or advantage for this kind of arrangement. You see, this trapezoidal MMF wave is much nearer to the sinusoidal wave compared to the rectangular MMF wave. This is your rectangular MMF wave. So if you compare this rectangular MMF wave with a sinusoidal wave, you see that they are very much different. But if you compare this sinusoidal MMF wave with respect to this trapezoidal MMF wave, it is not sinusoidal, agreed, trapezoidal MMF wave is not sinusoidal, but it is very nearer to sinusoidal approximation compared to this rectangular MMF wave, isn't it? So that's why we can actually we go for distribution of coils along the stator core periphery. So let me then just throw some light on this particular aspect, that between the term electrical and mechanical degree over here, please note down that if theta is only written, if theta is only written, then that is your in electrical degree, and if theta mechanical is written, then that is your mechanical degree. So what is mechanical degree? Mechanical degree is what you can see with your bare eyes. So what do you see here? That the nature of magnetic flux density distribution along the air gap periphery, or simply speaking, the space distribution of magnetic flux density B along the air gap periphery is assumed to be sinusoidal like this. What is the reason for this? The reason has been told earlier. What is that? We have said that we are applying Fourier series expansion to this rectangular MMF wave. So if you apply this Fourier series expansion to the rectangular MMF wave, it will have one fundamental component and harmonics. So we are ignoring or we are neglecting the harmonic component. So only fundamental component is remaining, and that is your sinusoidal component. So that's why we say that the nature of magnetic flux density distribution along the air gap periphery is sinusoidal, because we are ignoring or we are neglecting the effect of space harmonics. Now, what is the actual meaning of this sinusoidal flux distribution or sinusoidal distribution of magnetic flux? The thing is that let us start from this particular point. So we are over here. Please follow the mouse pointer. So we are in front of the coil side, which is carrying cross current. So we are in front of the coil side on the stator core. We are in front of the coil side on the stator core, which is carrying cross current. That means theta mechanical equal to 0 degree. So over here you will find that magnetic flux density is 0. Why magnetic flux density is 0 over here? Because for this point you will see that magnetic lines of flux are neither leaving nor they are entering. So this point is that point along which you will find that no magnetic lines of flux are either leaving or entering. Nothing is happening. Lines of flux are neither leaving nor entering. So at this particular point, at theta mechanical equal to 0 degree, at this particular point, at theta mechanical equal to 0 degree, you will find that flux density value B is 0. So that is your 0. Theta mechanical is 0. Now if you move away from this point, you please follow the mouse pointer. If you start moving from this point, let's say you have come over this point in front of this north pole, which is developed on the stator core. So let's say theta mechanical, this point is nothing but theta mechanical equals to 90 degree. You can view in the diagram that this particular point is that point in the air gap which is at an angular distance of 90 degree. This point in the air gap in front of the north pole center, in the this point in the air gap in front of the north pole center, is at an angular distance of 90 degree from the reference axis. That means theta mechanical is 90 degree here. Now what you will find that most of the magnetic lines of flux are directed along this particular point. So this point is that point where the magnetic flux density is maximum. So this point is corresponding to this point. Likewise, if you come over here at theta mechanical equals to 180 degree, if you come over here at theta mechanical equals to 180 degree, you will find that the same thing is happening. I mean to say, neither the neither the magnetic lines of flux are leaving or entering this particular part on the stator core. This particular portion on the stator core, or simply you just uh, try to view the point in the air gap which is in front of the coil side, which is carrying dot current. That means let us focus our attention on that coil side which is placed on the stator core, and it is carrying dot current. So if you choose a point in front of that coil side, you find that at this particular region, at this particular point, magnetic lines of flux are not present. Simply speaking, at this particular point, magnetic lines of flux are not present. So this is that point where magnetic flux density would be zero. Likewise, if you come to point theta mechanical equals to 270 degree, you will find that most of the lines of flux are passing by or crossing this point in the air gap periphery, which is at theta mechanical equals to 270 degree. So over here again you will have that maximum value. Now what we have done, we have chosen a simple convention that flux under the north pole on the stator core will be treated as positive, and flux under the south pole on the stator core will be treated as negative. Or this can be placed in another way. What is that? If magnetic lines of flux are leaving the stator core and entering the rotor core, those will be termed as positive. So under north pole on the stator core, what is happening? Lines of flux are leaving the stator core and they are entering the rotor core. So that's why this flux will be treated as positive. And if lines of flux are leaving the rotor core and entering the stator core, then that will be treated as negative. So that's why magnetic lines of flux under south pole will be treated as negative. So accordingly, you will have positive maximum at theta mechanical equals to 90 degree, and you will have negative maximum at theta mechanical equals to 270 degree. This is as per our convention. Or we can simply say that flux under the north pole is positive and flux under the south pole is negative. So north pole will give positive value of flux density and south pole will give negative value of magnetic flux density. Now you must have noticed that the induced EMF E in the single conductor is having the same waveform as that of the waveform of the magnetic flux density. Now why is it so? This is because you see EMF induced in a single conductor is given by BLV, where B is the magnetic flux density, L is the length of the conductor, and V is the tangential velocity or the peripheral velocity of the conductor. Now, why we are using this particular word, tangential velocity or peripheral velocity? Because you see our conductor, which is shown by a purple color dot on the rotor, we are thinking of a conductor which is placed on the rotor and it is indicated by purple color dot. So this conductor will move around the air gap periphery and it will encounter different value of magnetic flux density. For this particular snapshot, the conductor is at that point in the air gap periphery where magnetic flux density is 0. So for this position of the conductor, EMF induced would be 0. But the rotor is not stationary, the rotor is rotating. You can find the arrow which is indicated on the rotor. So rotor is rotating in the clockwise direction. So let's say rotor is driven at a uniform speed in the clockwise direction. So what will happen? The tangential velocity or the tangential speed for the conductor which is placed on the rotor will be also constant. Tangential velocity is simply found, you can simply find the tangential velocity V for this conductor which is placed on the rotor by using the formula V equals to pi d n, where d is the diameter of the rotor and n, which is actually small n, is the speed of the rotor in rps, that is revolution per second. So using the formula V, that is peripheral velocity, V equals to pi d n, where d is the diameter of the rotor and n is the speed of the rotor in rps, that is revolution per second. So if the rotor is driven at uniform speed, then peripheral velocity for the rotor conductor is fixed, that is v is a constant, length of the conductor is fixed. So what we find out? that induced EMF E in the conductor which is placed on the rotor will depend only on the value of B, that is magnetic flux density, because L, that is length of the conductor, is constant. V, that is peripheral velocity, is also constant, because peripheral velocity is given by pi dn. D is the diameter of the rotor, n is the speed of the rotor in rps. So we say that the variation of induced EMF in the conductor which is placed on the rotor, that is small e, the variation of small e will be exactly same as that of the variation of the magnetic flux density. That means whatever is the waveform, or whatever is the nature, or whatever is the waveform for the variation of magnetic flux density in the air gap periphery, that would be the variation of induced EMF in the conductor which is placed on the rotor. That means waveform for B, magnetic flux density, and waveform for induced EMF E in the conductor would be exactly same replica of each other, because L and V are constant and B is the thing on which induced EMF is going to depend, because E is given by BLV. Now, we were till now only dealing with the case where number of poles developed on the stator core was 2. But if the number of poles developed on the stator core is, let's say, 4, like this one, so for this, what will happen? You will find that as per our convention, flux under the north pole is positive, flux under the south pole is negative. So you have two number of north pole and two number of south pole on the stator core. So what can you do? You can start from theta mechanical equal to 0 degree. So if you take this point, you may follow the mouse pointer please. So if you are taking this point in front of the coil side which is carrying cross current, and that coil side is placed on the stator core, and also that point is lying on theta mechanical equal to 0 degree. That means this particular point, the point which is on theta mechanical equal to 0 degree, here again the same thing you can observe, magnetic lines of flux are neither leaving or entering for this particular point which is at theta mechanical equal to 0 degree. So here B value, magnetic flux density, is 0, but at this point at theta mechanical equal to 45 degree, magnetic flux density is maximum, and it is also positive maximum as per our convention, because the convention which we have adopted, for that convention, flux under the north pole will be coming to be positive and flux under the south pole will be coming to be negative, according to the convention which we have adopted. So at theta mechanical equal to 45 degree, there is a positive maximum. Again at theta mechanical equals to 90 degree, there is 0, because you see, if you take this point which is lying on, if you take this point which is lying on theta mechanical equals to 90 degree, you will find no lines of flux are entering or leaving. So this point is that point where magnetic flux density is 0. Now, if you come to this point, theta mechanical equals to 135 degree. So, if you choose a point on the line which is equal to how much? Theta mechanical equals to 135 degree. Here, the magnetic flux will be maximum, but since it is under the south pole, so according to our convention, it will be negative maximum. Like at theta equals to 180 degree, it will be again 0. So, you see, one complete cycle has been covered in a span of 180 degree mechanical. That means we have moved only from theta mechanical equal to 0 degree to theta mechanical equals to 180 degree. But in that 180 degree span, I mean to say, when we are moving 180 degree in terms of mechanical degree, we are seeing that one complete cycle of the variation of magnetic flux density has been completed, isn't it? Like this one, you can view over here. So you can see that for theta mechanical equals to 180 degree, please follow the mouse pointer. For theta mechanical equals to 180 degree, you see one complete cycle of variation of magnetic flux density has been completed. So if we complete the movement from theta mechanical equal to 0 degree to 360 degree, so that way two cycles of flux density variation would be completed. So for theta mechanical equals to 360 degree movement, that means you start from this point at theta mechanical equal to 0 degree, you start from this point at theta mechanical equal to 0 degree, and you again move on, and you again return to the same position. So mechanically you have moved by 360 degree. Mechanically you have moved by 360 degree, but for that 360 degree movement along the air gap periphery, you would find that there are two number of positive peak and there are two number of negative peak, because north south will give you positive peak, negative peak, then another pair of north south will give again positive peak and negative peak. So you get two positive peak under the two north pole which are developed on the stator core. You get two negative peak under the south pole which is developed on the stator core. So you have actually completed variation of you have actually completed the variation of two cycles of two cycles of magnetic flux density variation for 360 degree rotation mechanically along the air gap periphery. So we say that two cycles of induced EMF in conductor placed on the rotor. Now, till now we are only seeing for one conductor portion. Till now we are only seeing for one conductor portion, but let's see what will happen if we are thinking of a coil. So you can please have a attention on the diagram. You can see now that on the rotor there are two purple colored dot. So these two purple colored dot, they are trying to indicate that it's a single coil, and this single coil is having two sides. So this is a one coil side and this is your another coil side. So for this coil also, the induced EMF variation will be like this only, because whatever is seen by this coil side, the same thing is going to be seen by this coil side also. So the nature of induced EMF in the coil would be sinusoidal, because we have assumed that the flux density distribution, what we have assumed, that flux density distribution in the air gap periphery or flux density distribution along the air gap periphery is sinusoidal. So that's why induced EMF E will be also sinusoidal in the coil also. There will be only one difference, that if one coil side is under say north pole, then another coil side would be under the influence of south pole. So let me tell you one thing is that for this particular diagram, it would be easy to find out that the relationship between electrical and mechanical degree is given by theta equals to 4 by 2 into theta mechanical. Now you see this is a 4 pole case. That's why it is written as 4 by 2 into theta mechanical. Had it been a p pole machine, then it would have been p by 2 theta mechanical. So a full pitch coil is that coil which is having its coil side at the center of the north pole and at the center of the south pole. So that is the meaning of one full pitch coil. So if this coil side is under north pole, so for this induced EMF polarity is like this. Let's say this portion is plus, this portion is minus. So for south pole, the induced EMF polarity should be opposite with respect to the north pole. This is because you see the direction of B, that is magnetic lines of flux, they are different for north pole and south pole. Let me take you to this particular diagram. You can see over here, what do you see, that the magnetic lines of flux under the north pole are directed away from the north pole phase. So the direction of magnetic flux density vector B would be directed away. Whereas for south pole, what do you see? For south pole, you see that magnetic lines of flux are directed towards the stator core, that means towards the south pole phase. So for this, the direction of B would be opposite with respect to N. So that is why we say that the induced EMF polarity would be opposite for south pole. I mean to say, induced EMF polarity would be opposite for those conductors which are under the south pole compared to the conductors which are under the north pole. So that's why the induced EMF voltage, the polarity of induced EMF for the coil sides, the polarity of induced EMF for the coil sides, that is plus and minus, for those conductors under north pole and for those conductors under south pole, they are shown opposite, because they are having direction of B, that is magnetic flux density, opposite for north and south pole. Although the direction of peripheral velocity v, direction of peripheral velocity v would be same for both the coil sides, because both the coil sides are placed on the rotor. So peripheral velocity is same for both the conductors. Only thing can vary is the magnetic flux density. That means the direction of, actually the direction of magnetic flux density, that is B. So actually that is not going to be a problem for us. That means if the polarity of induced EMF for the conductors under north pole and polarity of induced EMF for the conductors on the south pole, if they are opposite, that is actually adding to our advantage, because when you take the algebraic sum of the voltage along the two coil sides, it will get added up. That means let's say we are starting from here. Please follow the mouse pointer. So we are starting from here. So this is the negative terminal. So negative to positive, there is a rise. So we will write plus 2 BLV. Again, when you move from this side to this side, again you are encountering negative to positive. So again there is a rise. So you write 2 BLV. So you will have 4 BLV. Since this is a double turn coil, so it is having 4 BLV. Now, why 2 BLV? Because you see, it's a double turn coil. So since it is a double turn coil, so you will have two conductors on two coil sides. So that's why BLV for one conductor, another BLV for this another conductor. So since this is a double turn coil, so you have got two conductors. So BLV for each of the conductors. So EMF induced on this coil side, which is under north pole, is 2 BLV. Likewise, on this side also you have got two conductors, because it is a double turn coil. So BLV for this conductor, another BLV for this conductor. So 2 BLV for this conductor. So you get added up and you get 4 BLV. Now you can simply use your unitary method to arrive at the result that if this coil would have been n turn coil means the coil is having n number of turns. So for n turn coil, what will happen? There will be n number of conductors on this coil side, there will be n number of conductors on this coil side. So since the coil is having n number of turns, so n number of conductors under north pole, so induced EMF will be n BLV. N number of conductors under south pole, so EMF induced will be n BLV. So if you add, it will get 2n BLV. So let me just quickly tell you that EMF induced in a conductor is given by E equals to BLV, where L is the length of the conductor, V is the velocity of the conductor, and B is the value of the magnetic flux density. Now, if the EMF is induced in a single coil having a single turn, so it will be 2 BLV. But if it is having n number of turns, then it will be 2n BLV, as explained earlier. Now, what is peripheral velocity? Peripheral velocity V is given by pi d n. Now we are writing n mechanical so as to make the things very clear to us, that when we are writing this RPS, that is speed of the rotor, then that speed of the rotor is actually the mechanical speed. So that's why we are writing n mechanical. Now for this coil, you can see that for this coil, the terminal voltage, that means voltage which will be available across the terminal A and A dash, the voltage which will be available across the terminals A and A dash would be given by 4 BLV in case it is a double turn coil. But if it is a n turn coil, so it will be given by 2n BLV, because there will be n BLV EMF induced for this coil side, and there will be n BLV EMF induced for this coil side on the south pole. So when you take the algebraic sum, it will get 2n BLV. So that is what written here, 2n BLV. Now you simply substitute the value of the peripheral velocity, that is pi dn mechanical, and you substitute the value of B. What we have seen, that the flux density B is changing in a sinusoidal way along the air gap periphery. Flux density B is changing in a sinusoidal way along the air gap periphery. So it is given by B max sine theta. So B max sine theta is the expression for flux density in the air gap. So we are writing that we are writing B max sine theta for small b. So for small b, we have written B max sine theta. For peripheral velocity V, we have written pi d n mechanical. And rest of the terms are as usual, n, l. So now let me try to express what we want to find is that this particular expression of induced EMF in the coil, single coil, but it is a multi-turn coil. It is a single coil, one coil, but it is a multi-turn coil. That means it is having n number of turns. What we want to know, we want to find some another expression. This expression is okay, it is fine, but we want to find the expression of induced EMF in a single coil having n number of turns in terms of flux per pole. So what we want to know? We want to know the we want to know the value of flux per pole. So how to find the value of flux per pole? For finding the value of flux per pole, let us take a strip of small area. That strip of small area is very small, infinitesimally small. So we are considering a strip of area on the rotor surface. We are considering a strip of area on the rotor surface which is infinitesimally small, and that small area is subtending an angle d theta mechanical at the center of the rotor. So basically we are trying to find an expression, mathematical expression, which will give you the value of flux per pole on the rotor surface. So for that purpose, we are choosing a very small area on the rotor surface, and that small area is infinitesimally small, it's very small, but that small area is subtending an angle at the center, which is how much? D theta mechanical. That is this angle subtended. D theta mechanical is the angle subtended at the center by this infinitesimally small area. So what is the area for this strip? We are only finding the area on the curved surface of the rotor. Let us take note of this fact that we are finding the area only on the curved surface of the rotor. So that is given by nothing but your length. What is the length? That is L. What is this arc? This arc is nothing but radius into angle subtended at the center. So what is the radius? Radius is d by 2, because d is the diameter, so radius is half of that. So d by 2 is the radius, and d theta mechanical is the angle at the center. So what is the length of this arc? This arc will have length r into theta. That means d by theta. That means d by 2 into d theta mechanical. So what is the area of this strip? The area of this strip is given by your nothing but d by 2 into d theta mechanical into L, where L is the length. So you can again have a look for the diagram. This is the length, and the arc which is developed by this small area is given by d by 2 multiplied by d theta mechanical. So we are actually considering this strip of area on the rotor surface as a rectangle, because it is very small, infinitesimally small. So this strip of area on the rotor surface can be considered to be a rectangle, because arc, this arc is very small, so it can be approximated by a straight line. So the length of the arc is given by d by 2 into d theta mechanical. So this is one side and L is the another side. So what is the area of this infinitesimally small strip? What is the area of this infinitesimally small strip on the rotor surface? It is given by nothing but d by 2 into d theta mechanical into L. But if I want to know that what is the flux which is encountered by this small strip on the rotor surface, we want to know what is the flux which is encountered, what is the flux which is encountered by this small strip on the rotor surface. It is nothing but d phi. Now what is the value of d phi? D phi is what? Flux is what? Flux density into area. So flux is your flux density, that means B into area. So area we have already computed, d by 2 into d theta mechanical into L. That is the area of this strip on the curved surface of the rotor. So this is the area of the strip on the curved surface of the rotor. We are not taking this area. We are only taking the area which is on the curved surface of the rotor. Now what else? The value of B, that is magnetic flux density, the value of B, that is magnetic flux density over this elemental area would be how much? It would be given by B max sine theta. Why B max sine theta? Because we have chosen this small strip of area at a theta degree away from the reference axis. That means along the reference axis the value of magnetic flux density is 0. Along the reference axis the value of magnetic flux density is 0, and we are choosing this strip on the rotor surface at a theta degree away from the reference. So that's why the value of magnetic flux density for this small strip would be given by Bmax sine theta, because it is chosen this strip of area, this particular strip of area on the rotor surface is chosen theta degree away from the reference. So that's why the value of magnetic flux density over this strip of area on the rotor surface would be given by Bmax sine theta. So that can be written for Bmax sine theta. And these are the some of the simple manipulation. We are rewriting the equation like this. You see, we have considered the angle which is subtended by this area at the center in terms of mechanical degree, because it was said to be d theta mechanical. So we have converted this angle d theta mechanical in terms of electrical degree by using this relation theta equals to p by 2 theta mechanical. So what is theta mechanical? 2 by p into theta. So we have written 2 by p into theta for d theta mechanical. So after that we can write for small b Bmax sine theta, as said here, that Bmax sine theta is the value of magnetic flux density over this strip of area. So we can write that Bmax sine theta. So now we have written that Bmax sine theta. Now what we want to know? We want to find the flux per pole. Now, what is the span of a pole? The span of a pole is 180-degree electrical. The span of a pole is 180-degree electrical. It can be easily viewed from this kind of diagram. You see, the span of a pole is 180-degree electrical. This is your mechanical degree, but if you calculate in terms of electrical degree, you have to multiply by 4 by 2, so it will come as 180 degree. So this was under North Pole, this was under South Pole, this was under North Pole, this was under South Pole, isn't it? So for one pole we mean a span of 180 degree. So that's why we will integrate this thing. That means first we have found the flux which is passing through the infinitesimally small area on the rotor surface. So what we have done, we have found the flux which is passing through this infinitesimally small area. So we have found out the flux which is passing through this infinitesimally small area, that is our d phi. But we are interested in knowing the flux over one pole, or rather what is the flux per pole. So that's why we need to integrate the flux over the area which is stretching for one pole. But one pole means what? Electrically it is 180 degree. So our limits of integration will be from 0 to pi. So if you integrate, you will get this particular expression. Now this particular expression of flux per pole will guide you that we can write P phi by 4 RL instead of Bmax. You can have a look. We have written here flux per pole, that is phi, to be 4 Bmax L RL by P. So this can be rewritten in terms of other constant equals to Bmax. That means Bmax can be expressed in these terms, in terms of number of poles, flux per pole, length of the rotor, radius of the rotor, that is small r. So we have replaced this capital D, that is the diameter of the rotor, by 2r, that is the radius of the rotor will be r. So diameter is D. So D equals to 2r. So we have simply substituted the value of this flux. We have substituted the value of Bmax actually. We have substituted the value of Bmax. Where we have substituted the value of Bmax? In the expression of this one. This we have derived earlier. You can have a look. This thing we have derived earlier. For a single coil, EMF induced is given by this 2 pi NLD N mechanical Bmax sin theta, and thereafter we have derived an expression for flux per pole. So we are expressing the Bmax in terms of flux per pole, and we are substituting this P phi by 4 we are substituting this P phi by 4 RL in this equation of Bmax. So we get this one. So after making some manipulation, you will have this kind of result. So you can have you can just view over here that we are only substituting P phi by 4 RL in place of Bmax in the above equation, and thereafter we are making some simplification. Yes, we are replacing the diameter by 2r, and we are making that substitution, that n mechanical, 2 pi n mechanical will be nothing but omega mechanical, because 2 pi n is nothing but the speed in radian per second, and since this n is the speed in mechanical revolution per second, rps, so that's why it is omega mechanical we have written. So for this 2 pi n mechanical, we are writing omega mechanical. For 2 pi n mechanical, we are writing omega mechanical. And thereafter what we have done, we have used that particular relation which we have derived earlier, that theta is nothing but p by 2 theta mechanical, where theta is in electrical degree. So if you take the time derivative, it will come like this: omega equals to p by 2 omega mechanical, where omega mechanical is the angular speed in mechanical radian per second, and omega is the speed in electrical radian per second. Because whenever you multiply by p by 2, you are multiplying omega mechanical, you are multiplying omega mechanical by p by 2, so that will be converted in terms of electrical radian per second. So you can write omega mechanical to be 2 by p into omega. So you make that substitution for omega mechanical, you will get this expression of emf induced in a single coil having n number of turns. Now once you get this, you can further simplify and you can cancel the terms which are there in the numerator and denominator. So you will end up with this particular expression. Now for theta, we are writing omega t. Why we are writing omega t? Because you see, as the rotor is rotating, the angular value, that is the theta mechanical, is changing. But that theta mechanical we have already replaced by omega electrical in the beginning only. Over here you can see that theta mechanical has been replaced by omega, which is in your electrical radian per second. So what we say, that after time t has moved by theta electrical radian, and if omega is the angular speed in electrical radian per second, then omega t will be equals to theta. So theta is replaced by omega t. You use the simple concept that distance traveled equals to speed into time. So what is the angular speed in electrical radian per second? Angular speed in electrical radian per second is omega. Angular speed in electrical radian per second is omega, and t is the time. So time into speed is what? Angular distance. So what is theta? Theta was the angular distance which is traversed in time t. So theta is replaced by omega t. Now, if you want to find the RMS value of the induced EMF, you have to simply you have to simply divide the maximum value by root 2. So maximum value is what? Omega n phi, because the maximum value of sine omega t can be 1. Sine omega t can be maximum 1. So we are dividing the maximum value omega n phi by root 2, we get the RMS value. So this is the RMS value. Now it is of very great concern that you should notice that this induced EMF has been derived for a single coil having n number of turns. But what would be the case if you have, say, more number of turns? I mean to say, let's say you are having uh, 6 number of coils, and they are distributed along the stator core or rotor core periphery. So in that case, how this expression is going to be changed? You simply find what is the EMF induced per turn. Per turn means, if you think of if you think of a situation where the coil is having only one turn, so in that case the value of n will be 1. So it is omega phi by root 2 for single turn coil. And if the number of coils are 6 and they are distributed, then you multiply by that, and of course you have to multiply also the distribution factor, because if the coils are distributed, there will be reduction in the induced EMF because the coils are distributed. So that distribution factor would be also taken into account. So I stop over here. Again, I will continue from this point only in my next class. So if you have any question, you can ask me.